All right. Welcome to a new pattern, day 63, and we're discussing backtracking. Uh, Backtracking is a technique that explores multiple paths to find a solution. Okay, multiple paths to find a solution. It builds the solution step by step by increasing values with time and removes the choices that don't contribute to the problem solutions based on constraints. Now, if you've been following this series, we've used backtracking a few times, and it's almost always, I think, or every single time, involves recursion in one way or form. I'm not sure what you're seeing right here, so I'm not going to mention it. But if it makes sense to you, good on you. But it didn't really make sense to make this statement didn't really make sense to me, so I'm gonna skip it. Now, the way it works is it first explores one possible option. If the required criteria have been met with that option, we choose a path that stems from that option and keep on exploring that path. Now, if a solution is reached from that path, we return the solution. Otherwise, if a condition is violated from the required set of conditions, we backtrack and explore another path. Now, it's better than brute force, since we don't have to generate all possible solutions and choose our required solution from among them. We have the option to check our required condition at each possible recursive call. If the condition is met, we continue exploring that path. If it isn't, we take a step back and explore another path. In this way, we avoid generating redundant solutions that brute force methods are known for. So this is what it looks like. Let's say we're looking for a path. We start with the initial set of values. Is the condition met here? No. Okay, I mean, yes, in this case, the condition is met, so it doesn't violate. Well, not that our final condition is met, but our current condition doesn't violate our final requirement. So we increment the value, move to the next node. Then, oh, look at that. We found something that doesn't work. We go back. We now check here again. Oh, it doesn't work. So we've checked all the children of these. We now go back to the parents and come to the sibling, and so on and so forth. This doesn't work. And then finally, we find something that works. We don't need to check this out. We've checked all these. If it was brute force, we still check these out, but we're done in this case. And now here's some examples. Find a path of ones from the top left to the bottom right in an n by n binary maze. And I think I'm going to go into this in one of the videos, so I'm not going to waste so much time explaining this. Check if a knight can cover all possible squares once in an n by n chessboard. I believe might go through this again, but you can look up this problem later, or I might do it down the line in one of these days, depending on what is scheduled for us by these guys. So depending on what appears here. So how do you know if it matches your problem? So this is a huge wall of text. Is it worth reading? Yeah, sure, why not? I have a few minutes left. So if you're constructing any solution, all paths must be explored. Then you know, oh, if I need to explore possible solutions, then I should be thinking backtracking. If you reach a dead end while you're exploring, you need to move back one level and explore all other paths. So this is one example problem. Determine whether an undirected graph can be colored using no more than n colors in such a way that no two adjacent vertices share the same color. Another way to know if we need this pattern is we need to consider all possible solutions in order to select the best one. So while solving such a problem, not a single feasible solution may be ignored. So we're checking every single thing, like in brute force methods. In certain problems, even if some feasible solutions are eventually discarded, we still need to find and evaluate them. So an example, select elements from an array of strings and concatenate them such that the concatenated strings is of the maximum possible length and contains unique characters. Another case is where the problem requires us to compile a list of all feasible solutions. An example, partition a given string into substrings so that each substring is a palindrome. We need to determine all possible ways in which the partitioning can be done to obtain palindromic substrings. And know if this problem structure, we don't need this pattern, the problem structure is such that while constructing a candidate solution, failing to meet the acceptability criteria of the solution eliminates all other possibilities within that solution. So we don't need to check the remaining possibilities. So this is an example of something that might look like, oh, it's a backtracking problem, but it actually isn't. That's what they're trying to say here. So given a set of integers and a target sum, determine if any subset of given integers can sum up to the target sum. The nature of the problem is such that once we find a subset that sums up to the target, there is no need to continue exploring other subsets. Similarly, if we reach a point where adding any additional element to the current subset would result in the sum exceeding the target, there's no need to explore any more possibilities for that subset. So here are some real-world problems with this pattern. So we use it for constraint satisfaction problems. So solve puzzles like Sudoku, where we enter a number into a cell. You know the game of Sudoku. Backtrack if it violates the rules and try again to find a valid path that satisfies the conditions. And then recursive descent parsers. This is like programming language theory and engineering. So the compiler takes a path through the grammar and reaches a point where the incoming tokens no longer match that part of the grammar. Therefore, the compiler backtracks to a point where there is another path through the grammar and follows that. This can occur several times so the compiler finds a grammar path that fits the incoming tokens, in which case it accepts the construct. If it finds no matching path, a syntax error has occurred. Yeah. So we're going to do the matching game. Always to place 5x5, 5 queens on a 5x5 chessboard. Backtracking, flatten binary trees, some other pattern. Maximize the revenue. We can make like cutting up a rod. This sounds like backtracking. Calculate the median from a data stream. We've done this before. It's a 2-heap pattern. You can go back in the videos and find it. I know that it's not backtracking. So yeah, and we have the different varied explanations. You can pause and review at your leisure. Thank you so much. See you in the next video. Bye-bye.